Tim Turson.
Leon Ferguson.
Jose Ramos.
We are environmental engineering students. This is the fall of 2011 and this is our senior design project.
Alright guys, what we got right here is an ion exchange unit. It consists of two columns. It's got a cation column and also an anion column. Before we could start doing it at all, we needed some water. So Swiss Clean Water Group was nice enough to give us some feed water we can start testing on. The first thing to do with the water was take it straight to the lab. There we found the pH, the alkalinity, the hardness, the solids. Once that was found out, we could go straight into the other lab and find the cations and the anions present in the water. Those are parameters we really needed to be able to design the column.
Now we will talk about ion exchange. Ion exchange is the exchange of an ion between two substances. Ion exchange units are known largely as water softeners, removing hardness causing ions such as calcium and magnesium. They also have the ability to remove nitrates, sulfates, and other metals from water. Cation resins, such as the one here, exchange hydrogen for cations of water such as calcium, magnesium, potassium, and sodium present in our water sample from Swiss water. Similarly, anion resins exchange hydroxide for anions in the water such as sulfate and chloride. Here's some anion resin right here. If built correctly, our ion exchange unit will clean out the ions from water and the final TDS will be significantly lower than what we started with.
Water from Swiss Clean Water Group, we were able to come to the lab and test the water. The first thing was to do, we had to test the water for the pH. So we just grabbed the pH meter, put the water in a beaker, measure it. We got on average around 8.3 for the pH. The second test we had to perform was a solids test to find the total solids, total dissolved solids, and so on. That we just needed some vials in the oven. Boom, it was done. The solids values came down really low, so that showed that we didn't really have much solids, so our system could run clean without putting any filtration or anything on it. Another test we had to do was alkalinity to find out. We used a titration method for that, and we got a value of around 122.6 milligrams per liter as calcium carbonate. Finally, we wanted to determine hardness. The main reason to determine hardness is to find concentration of calcium and magnesium in it. For hardness, we also did the titration method. We had an indicator. We found the final endpoint. Hardness, the total hardness was around 127.3 milligrams per liter, which gives around 32 milligrams per liter of calcium and around 11 milligrams per liter of magnesium.
Next part of our water analysis included analysis by ion chromatography. Right here is the setup that we used to test our water. The water sample came from Swiss Water Company. Right here on the computer is a Chromoleon software. This is the thing that runs the whole unit and tells the unit what to do. To do this lab, you take a solution, put it in a vial as shown here. You go ahead and insert that vial into the auto sampling machine. Through the software, it will tell the machine what vial to take a sample of and do a readout on the computer screen as shown. The y-axis includes column activity and the x-axis is time. Each of our cations that we test for have a different retention time, and by that we can know which ion it is. The readouts that we got are right here. This first peak is sodium, the second peak is potassium, the third peak right here is magnesium, and the fourth peak is calcium. We got concentrations of 94.39 milligrams per liter for sodium, 11.96 milligrams per liter potassium, 11.12 milligrams per liter magnesium, 37.82 milligrams per liter for calcium. The magnesium and calcium concentrations lined up with those done in the hardness lab.
I'm going to talk about the breakthrough experiment, which is what we had to do before actually designing the full-size model. Here is our scaled-down version. This is the anion column. This is the cation column. The resins are going to be held in place so that they don't escape with the flow, and they're held by a polyethylene filter that was provided to us by Resin Tech, which is the same kind of filter we're going to be using in the larger columns. For the experiment, we used this Masterflex pump, pumping at a flow rate of 0.182 liters per minute. Our first experiment didn't go as we had planned. We prepared 2 liters of solution that was the same concentration as the feed water from Swiss Clean Water, which was about 315 milligrams per liter. We prepared the 2 liters and ran the system for 10 minutes and found that the resin had not yet exhausted. So we had to do a second run where we created more solution this time. We created 8 liters of the same solution, and we found that the resins were exhausted after 39 minutes of running this. The breakthrough point was at about 14.3% of the effluent of the initial concentration, so which was about 45 milligrams per liter. We use this information to calculate the amount of resin that we would need in our larger columns, and that the exhaustion time for the larger columns was going to be about 5 hours.
I'll be describing the specifications of our model. The Masterflex pump will be providing a flow rate of 0.3 gallons per minute. The pump is hooked up to a 3/4 of an inch clear pipe that adapts to a 1-inch male adapter. The design we have here starts off with 1-inch female adapter that connects to a 1-inch PVC 2.5 inches in length. After follows a 1-inch ball valve that is connected to another 1-inch diameter pipe 2 inches in length. Then we have a 1-inch diameter T. The T is followed by a 1-inch diameter pipe 2.5 inches in length. The pipe fits into a 1 to 2 reducer, and then comes a 2-inch diameter pipe that is 3.5 inches in length. Then we have a 2 to 4 reducer connecting to the acrylic column. Inside the reducer, 2 crates are holding the polyethylene resin filter in place. This filter keeps the resin from escaping with the water flow. The setup inside these reducers is the same throughout the system. The column itself is filled with anion resin provided by Resin Tech. After the 24 inches, 3.5 inches diameter acrylic column, we have a reducer from 4 to 2 inches again with the same specification as before. And then a 2-inch diameter pipe, 3.5 inches in length, and a PVC reducer from 2 to 1 inches. Then follows a 1-inch T that connects to a 1-inch diameter pipe to a 1-inch valve. The valve is followed by a PVC that connects to a 90-degree elbow, and then follows a 1-inch diameter pipe that is 41.5 inches in length. This long pipe connects to 2 columns in a series. After the 90-degree elbow, the same pipe configuration occurs, and the only difference is that the next column is filled with cation resin and the effluent leaves at the bottom.
To generate the system, we must first run water through the system all the way through it backwards from where it came. So that would be from outlet to inlet. And then after that, we have to close the valves so no water gets moved throughout the system, and we have to throw in the regeneration liquid. For the cation, we're going to use hydrochloric acid. For the anion, we're going to use sodium hydroxide. Once it's in there, we lock it again, so that way the regeneration liquid sits in the columns. Approximately, we want to have it for 40 minutes in the cation. We want to have it for 20 minutes in the anion. Once that is done, we can open the bottom and let the regeneration liquid exit.
So here's our initial concentration of our feed water. It's 342 going down ppm. It's going down the anion column here, and then down the cation column. We're going to test the effluent concentration.